Welcome to my presentation. I'm Bornträger. I'm the maintainer for S390 in KVM and QEMU together with Cornelia. Maybe you have seen the S390 parts already by Cornelia and David, so I'm here to do something different, not S390. The title is As Time Goes By, analyzing where we spend our cycles during exits. Let's talk about motivation first. This is actually something that did not happen due to a particular performance issue or some problem that our performance team found. It was more like a fun project, something that I like to do. And the quote by Linus is actually a quite good summary of why I did that. And I started that very early, basically 3 or 4 years ago. And micro-optimizing is certainly something that I did during that time. And I'm going to give you some parts of these things that I've worked on. 30 minutes is certainly not enough to do all the thing. So I hope that I choose the right parts, things that are interesting for you. When I did the presentation, I also asked myself, okay, I did all these micro-optimizations which can be seen in micro benchmarks, but what does it actually give you in a real-life benchmark? So I started with a UPerf TCP/IP round-robin workload where you send 1 byte into one direction and receive another byte back. And you basically have 2 guests running on the same host. And then I decided to, okay, let's add N delay after each guest exit. So whenever we exited the guest, I added some N delay with a configurable delay. And I looked what kind of performance you get for this specific UPerf benchmark. And the interesting thing is that if your hardware is really slow, let's say your hardware takes 30,000 nanoseconds for an exit, it's not even bothered to optimize other things because you're almost on the same performance level. But what's also interesting when you zoom in, that you actually can get small performance gain, let's say 1 or 2% when you optimize your exit time by 100 or 200 nanoseconds. So you get a slight performance benefit for that particular workload. So this is not completely irrelevant, and even small things might pile up in the end. So what did I do, basically? I wrote a kernel module for S390, which basically ran instructions where I knew that they will cause an exit from the guest. And then I measured the time before and the time after, and I did several thousand iterations, did the math, the average, and so on. And the initial round-trip time on my system back then, with the config that I had back then, on the old system that I had, was actually much, much higher than I would have expected it to be, knowing the time that the hardware actually takes doing guest exit. So by simply quickly looking at some kind of samples, just doing perf, I was able to identify a lot of things very easily and brought it down to 500 nanoseconds. And that is actually something that you can learn. Doing analysis and always look for the low-hanging fruits for new architectures, new chips, might give you actually a decent performance win pretty quickly. And then over time, you have to fight against new code that introduces regressions, makes things more expensive, and you actually find out that old code that has been there forever is actually much more expensive than you have thought of. Today I'm on 300 nanoseconds on my test system with my private kernel config, so this is a totally uncontrolled measurement. Any kernel config might change that number really heavily, so there's no value in comparing that to whatever. I have also some numbers for x86 on the next slides. Okay. Interesting thing is, this is still much higher than the hardware overhead that I know of. So, what else can you do to measure? Some of you probably know the KVM unit test, which is available for most platforms except S390. And you can actually measure the time that typical exits take. In that case, it gives you the amount of cycles, not the amount of nanoseconds. And there are basically three classes of things, instructions that you can see. There are instructions that are implemented in the KVM modules or handled in the host kernel. There are instructions which are handled by hardware. And there are instructions which are handled by QEMU. These are these three classes. And what you actually want is to have most of the instructions done by the hardware. That would be the perfect solution, of course, but that's not always possible. Then the next step was to actually find out why take a specific exit so long. So first idea was, there's ftrace, and you have all these kind of cool measurements, so let's use that. Then I looked at the function tracer, and the resolution of time was microseconds. And I talked about some 100 nanoseconds, so was not the ideal solution for my case. But there's a function graph tracer, which actually gives you nanoseconds for a specific function. So I started my measurement, and whoop, I realized that just enabling the function tracer makes that particular benchmark that I had 10 times slower, or even more than 10 times for the function graph tracer. So the ftrace has a much higher overhead than what we achieve in KVM for guest exits, which is actually quite impressive how optimized A, the hardware is in recent generations, and B, how optimized the KVM module is. I think this was a big surprise for me, how inefficient ftrace is in contrast to that. Still, ftrace is useful for finding interesting places to look closer. It has some other issues, like not all assembler files are prepared to do that, but what I did in the end was actually using perf top and perf annotate and staring at disassemblies. So I then looked closer at hot samples. There are some instructions which were very hot in these samples, and then I looked why. I also used handwritten hacks so that I can circumvent some code, and I disabled, let's say, optional code and retested. So what did I find during that time? One example is early exits. We have a lot of code that runs during a KVM exit, which has to run all the time. You have to check, is a timer pending? You have to check, is a vCPU request pending? And these kind of things. Is a signal pending? And whenever you have a chance, you should try to have an early exit. For example, in that case, the handle request function only checks for, I think, 4 or 5 requests on S390. But you have a test bit, you have a clear bit, and you have memory barriers. So all in all, the whole function, which is executed basically on every cycle of KVM, is quite expensive. And by just doing an early exit, if no request is pending, just don't bother about test bit and clear bit. You can actually speed up our exit reasonably well. There was a follow-up idea by Paolo to pull this check into the KVM check request function itself, so that GCC can optimize. First thing, I forgot about that proposal, so it dropped on the floor, and I was reminded about that when doing the presentation. But then I looked at x86 and Power, and they already have a similar thing. They actually do the same kind of request early exit. And I checked MIPS. They only have one request bit, which is probably not worth the effort there. And ARM sets 1 bit, but I have not found the code that actually checks that. So when I find out, I can certainly do the common code patch anyway. Another thing that I found out during that time, IRQ save and IRQ restore is much, much more expensive than IRQ save and IRQ disable and enable. In my case, I have 5 to 8, but on other hardware levels, I have even seen a factor of 20. So whenever you know in which context you are, don't use IRQ save, use IRQ disable and enable. It's really faster on most CPUs. And it turns out that we use IRQ disabling and enabling quite often. In KVM, we use it around guest enter and exit. RCU code might use it for some specific things. Inside some exit handlers, I found IRQ disabling and enabling. In the scheduler code, we have that. In KVM, we now disable enable instead of doing a save and restore. I did some early patches for S390 mostly, and Paolo basically extended that to other platforms. Okay, and then there have been more things in the S390 code. There's a tracing feature for most S390 kernel code. So I put then an early condition check into a header file, which then GCC could use to optimize very early instead of doing a function call, then doing a check and returning. The early exits, as I did for the request handling, we did similar things for the interrupt handling. Then it turns out that KVM built-in versus module also gives you some nanoseconds of performance. There are some kind of jumps between the kernel text and the KVM module. Another thing is that a built-in module can be backed by large pages because the kernel text segment and other small reasons. But that was also interesting that this was actually measurable, the difference. In the end, I even optimized the IRQ code in S390 to use instructions which have fast passes, which made everything faster. So let's look on where do we stand today. As I said, upstream S390 kernel, with my kernel config, I have 300 nanoseconds for a simple hypercall. So I did that measurement with one CPU in the host and the guest. So I was able to remove code that is not strictly necessary in that case. Turns out that the biggest chunk is actually time accounting. You probably know that we have the guest time accounting, where we account if it's a user time, system time, and guest time. And the architecture code and the common code is actually doing a lot of calculations and magic shifting around, and this seems to be quite a big chunk of code. Then I removed the IRQ disable enable around the guest enter exit because I know the worst case that can happen is that the numbers are wrong. So I was just interested in how much time do we spend there, and it gave me another 10 nanoseconds. Then I tried other things like removing locking, tracing. These things are really small, no big win. So then I decided to go for the big hammer. So I added a shortcut in the C code. If that specific exit comes, just short circuit and go back. And hooray, another 40 nanoseconds. So interrupt handling, request handling, all dropped, and also the handles, signal handling, whatever, gives you 40 nanoseconds. And it's still much more than what the hardware actually does. So I then went one step further, do a shortcut in the low-level assembler routine. So I did a check in there, avoided all the address space reloading, whatever, and yeah, another 25 nanoseconds. It's still larger than the pure hardware, but we are pretty close now. There are some things that actually explain why the measurement might take longer than what you see in the table of how long an instruction takes. Because you change context. So maybe there are some restarts in the pipeline necessary, or TLB or branch prediction has some hash collisions or aliases, whatever. So if a CPU has a guest exit, it will not run with full pipeline power. It has some bubbles. And of course, there are still some code in the hypervisor that needs to run. The assembler code was not empty. Okay, that was the kernel. So basically, we are actually pretty close to the optimal solution. It's not an order of magnitude. It's really pretty close. Next thing is QEMU. On Broadwell, we have about additional overhead of 3,000 cycles, or in my Ivy Bridge system here, 6,000 cycles. And there are lots of things which are known. Of course, the overhead that we have seen just now. Then there is a signal mask handling in KVM. Radam had some interesting patches that we might want to use for S390 to get rid of them. Then, of course, it's a system call return. KVM run is a system call, an IO control, and it will return to the glibc function. There's some kind of plumbing code. It will return to the KVM low-level routine, the main loop. Then you do, of course, the exit handling, and go back to glibc, enter the system call, and be back in guest, basically. And of course, we have even one more context switch: guest, host kernel, guest, host user space, so branch prediction, TLB, caches. And of course, there are some things which are horribly expensive in QEMU, which I will tell about later. First thing is, can we actually stay in the kernel for most exits? And this is basically the opposite of what Stephen Rutherford did for his split IRQ work. Can we do more in the kernel? And the question is, there are some implementations already which do that. When you look at the KVM exit, basically you are in guest context, and someone you haven't guest exit. If KVM can handle that, it will just re-enter the guest, or handle request and re-enter. If KVM cannot handle the request, it will exit to the QEMU thread, handle it there, go back to the KVM module, and then re-enter the guest. What is done for most I/O devices is something called eventfd. For I/O operations, for example, on the VirtuO device or whatever, you basically exit the guest, then the KVM module notifies a file descriptor and re-enters immediately the guest. And then the I/O operation is handled asynchronously. And that actually makes the exit handling much more efficient. When I used eventfd versus non-eventfd on S390 for a diagnose 500, which is the VirtuO cake function, basically, I was able to reduce the guest exit time from 1,400 nanoseconds to 400 nanoseconds. And the good thing is, then I tried with 100, 200, and 500 disks, that this actually seems to be quite constant, though. So eventfd seems to scale very, very well, which is good. So then I asked myself, okay, that side is certainly efficient. Is that also true for the other side, so the real performance? And it turns out, as long as the disks all have their own I/O thread, then it seems that the performance for FIO with some random read on a null block device is basically also independent from the amount of disks, which is good. So what can we do when we actually avoid most exits to QEMU and stay inside the kernel for the most important things? There's one thing that can be done, which is to defer certain things to a later point in time. for example, we know that the host kernel does not use floating point registers. So in KVM, we can actually avoid storing and restoring the floating point registers at guest exit time and defer that to a function vCPU load or vCPU put, which is called by the preemption notifiers or during normal operations. So, yes?
The preempt notifier still has the issue that it will restore the QEMU user space FPU context, even if we never need it.
That's true. There's even more room for improvement, but still the low-level handling gets improved. So the comment was that the preemption notifier restores the basically the user context, which might not be necessary. But this is certainly something that we can do because we have more exits in the kernel now. Okay, I said there are some horribly expensive things in QEMU. Are there any examples? This is something that Stephen Rutherford mentioned in his call. He actually tried to get the register content or the content of registers in QEMU. So you usually do that with CPU synchronized state. And that calls an architecture function, which then usually calls I/O controls to get the general purpose registers, floating point registers, and whatnot. And that also schedules a put register before re-entering KVM. So what does that mean on x86? You have basically two I/O controls per register class, a get and set for each exit. And you have to know that the system call is actually a pretty expensive operation. It's not that cheap. It takes 100 or 200 cycles. And if you have, how many are these? 16? 14? This sums up. So I did an experiment on the row 6 here with the KVM unit test. I used that specific exit, which took 9,000 cycles here, and I added CPU synchronized state just here in the generic KVM CPU exit function. And ta-da! Instead of 9,000 cycles, we have now 60,000 cycles, which is quite impressive. Good thing is, CPU synchronized state is by far not the most expensive operation in QEMU. Still, we want to get rid of that in S390 because on S390, we need the register content for almost every exit. For historic reasons, we have basically only one exit type, and a lot of parameters are in registers for specific instructions. So it's fair to say that when you have an exit on S390, you very likely call CPU synchronized state. So what we did was basically suggested by Alex as well, is to use a shared page between the kernel and QEMU to synchronize the registers over there. And so we have the sync-reg structure in the KVM run, where we basically have all the guest registers written on a guest exit, so QEMU does not have to call any I/O control anymore on S390. Is this good enough? Interesting thing is with all these optimizations, I can still see the put or get register function in the profile. Very low, but I can see it. And in that case, we have 32 vector registers, and due to the architecture, parts of the vector registers are merged with the floating point registers, so we have to copy them in 64-bit chunks. And due to alias rules and other things, GCC creates a loop with stores and loads instead of one big mem copy. And of course, there are some cache effects. We had the context switch and so on. So this is not totally cheap. So long-term solution might be just to have access functions for registers. As I said, it's not the CPU synchronized state is not the most expensive thing in QEMU. Another thing which is really surprising is how long it takes to resolve an object with the object model. So instead of adding CPU synchronized state, I just resolved some random value. And I have basically an overhead of 110,000 cycles for just resolving one specific object. Wow. I have not yet time to find out what's going on. It's working glib iter objects and working lists, whatever. So there's probably room for improvement in that area, and this is something I want to look in after KVM forum. Another thing where QEMU is expensive is the big QEMU lock. Until QEMU 2.4, basically everything was protected by a big lock. So whenever you exited the guest from KVM, you took the big QEMU lock. And with 2.4, some kind of push-down effort started to hold that specific lock less often. And I have here some example. The blue line is QEMU 2.3 on an Ivy bridge with 4 cores and hyperthreading. So I had eight logical cores. And I started the KVM unit test with the SMP parameter. So I had 1, 2, 3, 4, 5, 6, 8 CPUs. And you can see that starting with 4 CPUs, basically the exit got slower and slower. When you compare that with the QEMU 2.6, you see that this push-down effort really gives you an advantage. And this is actually probably worse than reality because, as I said, it's a 4-core system with hyperthreading. So I would assume that these last 4 elements are actually faster than what is printed here, if you had real 8 cores. Okay, what else can we do? Best thing is to avoid exits. That's what I've said on one of the first slides. So whenever there's a hardware feature to avoid exit, try to use it. Or suggest hardware features to the hardware team if you have the possibility. Or you might improve interfaces. For example, whether O has some kind of interrupt or notification avoidance. When you look at the kernel, there is actually not that much room for improvement. I will send a patch for the request handling to optimize that. We can certainly optimize the signal mask handling. But in QEMU, we can actually do more. We should look further for big QEMU lock pushdown areas. We have to understand why the object model is so slow. And we might want to optimize or avoid synchronized state. And we might even extend the event FD to other device types. Coming to my last slide, this laptop here is actually much faster as soon as I plug in power, in terms of cycles, not in terms of time. So it seems that the power-saving mechanisms of the Intel CPUs really do have some kind of magic things going on where they disable some optimizations or part of the chip. And I found 2 performance bugs in the S390 code when preparing these slides where I could actually optimize things and do things better. So time is up. We have still some minutes for questions. Thank you very much.
Basic question is, what was the clock speed of the machine?
It's hard to tell because I have measurements from x86 and S390.
No, for S390, sorry.
I think it was the 5 gigahertz.
Okay, so just that people can also relate the nanoseconds to cycles. But anyway, for QEMU, you were really testing the worst case of all because you were giving no path. So basically, it's going through the whole object tree to see if it's ambiguous. And if you have 2 of the type that you specified, then it would fail. So if you actually test the same thing like with /machine instead of just the empty string, it should be much faster. And the other question I had, can you go back? I tell you when to stop. Go back. The one where with a lot of numbers, like the nanoseconds on S390.
Okay. That
Yeah,
one?
this one. So the SRCU locking actually would expect a lot more because it has 4 memory barriers. So are memory barriers actually very cheap on S390?
Yes, I mean, we are a TSO platform, basically. So
No, I mean the full ones, the SMPMB.
We have no read and write memory barriers, and the full ones is basically just flushing the store queue.
So how many cycles, roughly, do you have an idea?
The instruction itself should be single cycle. It has a dependency on the following instruction. So it really depends on do you have lots of stores pending. So it can be really cheap.
Okay, because on an x86 it's like 50, so we actually see a lot the SRCU locking. Michael Sirking introduced the SMPMB memory barrier before SRCU unlock that's optimized the way, because that actually saved like 50 clock cycles on the... So
this is we have basically a slightly stronger memory model than x86,
yeah.
So the serialization is pretty cheap.
Yeah, it seemed to be very little, so that's why I was asking. Thank you.
Hi, sorry, I missed your first slide, so I don't know if you covered this or not. But on x86 specifically, did you have any different settings for your BIOS in terms of power profiling or P or C states or things like that?
Yes, I have more power saving on when the.
No, I don't mean about your laptop. I mean on the.
Oh, you mean as a suggestion or?
Yeah, no, on the measurements you made specifically regarding.
This was with power on and CPU scheduler, basically the CPU frag on a fixed frequency.
Right. So you didn't have turboing or anything like that going on?
No.
Okay. Yeah, it's just something to keep in mind, I guess, when you do these measurements. I've come across things like if you're measuring these exit latencies and you do that a lot, you notice they actually change depending on your processor type. Right?
I actually try to keep it on one clock speed to actually see differences between when I change things.
Yeah, that's normally what I'll do. Disable sleep states, everything. Yeah, that's it.
No more questions? So thank you.